We've been learning about decision tree learning, which is the process of creating or learning a decision tree given some training data. This decision tree can then be used to classify or predict a new problem instance. Recursive partitioning is the most common strategy that you can use for decision tree learning. It basically involves taking your training data and dividing it into subsets based on the value of one attribute. At each step, you would pick one attribute and divide your data into subsets based on that attribute. This attribute is chosen based on how homogeneous or pure the subsets are when you choose that as the attribute to split. ID3, C4.5, CART, and CHAID are a few different decision tree learning algorithms which are based on this recursive partitioning strategy. Now, the difference between each of these is that they use a different measure or metric for arriving at the best attribute. This metric is a way to measure the purity or homogeneity of a subset when you choose that attribute to split the data. ID3 and C4.5 use a method called maximizing information gain. CART uses a method called minimizing Gini impurity, and CHAID uses statistical significance. Each of these measures is a mathematical way to measure the purity or homogeneity of a subset and choosing the best attribute at each step of the recursive partitioning strategy. We'll go through each of these measures one by one. Let's start by understanding information gain. The idea of information gain is to reduce entropy, which is a mathematical measure, and maximize information. Both of these are mathematical concepts which were introduced by a scientist called Shannon in the context of digital communication, where messages are passed back and forth between transmitters and receivers. We'll first learn about information and then about entropy. Information is a mathematical measure for how much information a statement, news, or message contains. Now, intuitively, you will be able to understand that some statements have more information and some have less information. Let's look at an example to see what we mean here. So let's say you have to classify an animal as a giraffe or a hippo. So there are different data points that you might be looking for. Some are more important than others. For example, if you were told this animal has 4 legs, this is basically useless. Both giraffes and hippos have 4 legs, so this statement gives us no new information. It doesn't really help us in our guess for whether this animal is a giraffe or a hippo. On the other hand, if you were told that this animal is 10 feet tall, this is actually useful information because it tells you that the animal is very likely a giraffe. So, we seem to have understood that the values of some attributes give us more information than others. Now, there is a mathematical way to measure how much information an attribute is giving us. You can actually quantify and get a number to represent how much information an attribute is providing us, and this is exactly the idea that we are pursuing. So if some attributes give us more information than others, we can use that to say this attribute is more important and should be higher up in our decision tree. To understand this, let's take an example of a game where your opponent holds a card and you have to guess which card they hold. You are allowed to ask them yes or no questions. So you have to decide intelligently what questions you're going to ask them, because you want to minimize the number of questions you ask before you can guess the answer. What card does your opponent hold? What happens when you ask a question? You get some information. So you want to ask questions which maximize the information that you are getting from them so that you can ask less number of questions overall. Now, initially, there are 52 possible outcomes for your guess. How many cards are there? So, let's say you ask the question, is the card an ace? What will happen is that if the person answers yes, you'll be left with a certain number of cards to guess from. And if the person answers no, then you will be left with another set of cards from which to guess from. So, in one case, you're left with 4 possible outcomes. In the other, you're left with 48 possible outcomes. So if the person had answered yes, you would have eliminated 48 possibilities and you were left with only 4. On the other hand, if the person answers no, you would eliminate only 4 possible outcomes. So when you look at these two answers themselves, there is one answer that gives you more information. That is the answer yes. The answer no gives you less information because it doesn't reduce as many outcomes. It still leaves a lot of outcomes on the table. Now, the answer yes has one quality. It has a lower probability of occurrence. So the lower the probability of something occurring, the more information you get when that is the answer. The probability of yes is 4 over 52. The probability of the answer no is 48 over 52. The answer which is less likely to occur, the answer yes, to the question is the card an ace, is more interesting and has more information for our particular game. It helps us guess more easily which particular card the opponent is holding. In general, this is true. Whenever something is hard to guess, whenever it is less likely to occur, the more information you get when it occurs. In this way, information can also be thought of as how interesting something is. Think of what kind of news are more interesting to us. The ones that you wouldn't expect to happen. Someone having sextuplets, for example. That is something that is very unlikely to occur. So that news is very interesting to us. So information is inversely related to the probability of something occurring. So if X is a random variable that represents the answer to our question, the information content of X equals yes is minus log P of X. This is the mathematical formula, and it is a function whose value will be higher if the probability is lower. If your probability is 0.1, log of 0.1 is minus 1, minus of minus 1 is plus 1. If your probability is 0.01, log of 0.01 is minus 2 and minus log of 0.01 is plus 2. So this is a function that increases as your probability decreases. Note that the base of the logarithm doesn't really matter. You could use natural logarithm, base 2, base 10, whatever you want. But the basic function is minus log P of X. So the information content is a function, minus log P of X. This is a mathematical way to measure how much information a statement or message contains. Now the other mathematical context that we were interested in is entropy. Entropy is the uncertainty when you're trying to guess something. So if you were to guess what news you're going to hear before it happens, sometimes it's easy to guess and sometimes it's really hard. So if you had to guess, for example, what time the sun will rise, that's easy to guess. It's going to be somewhere around 6 a.m. for example here. This is a guess that has low uncertainty or low entropy. If you were to guess what the result of a coin toss would be, that's very difficult because there is a 50% chance that you will be wrong. So just like some answers have more information than others, some questions have more entropy than others. In fact, the mathematical measure for entropy is directly related to the mathematical measure for information. Think of information and entropy as being related this way. If information is a measure that is associated with the answer to a question, entropy is a measure that's associated with the question itself. And it tells you how much uncertainty there is in that answer to that question. Let's say you have a question which has a number of different possible answers. Each answer has some information which is given by minus log p of x. The average value of the information that you get with each answer, each possible answer, is the entropy. So the average value of the information content is given by this formula. So for each possible answer, take the product of the probability of that answer occurring and the information content in that answer. The sum of this will give you the expected value or the average value of the information that it's possible to get from that particular question. This is the entropy and it is denoted by this notation h of x. Entropy is, once again, the amount of uncertainty or unpredictability there is in the answer to your question. Entropy increases with the number of possible answers and the evenness of the probability distribution. The higher the number of possible answers, the harder it is to guess the answer. Therefore, the entropy is high. The more even the probability distribution, the harder it will be to guess which particular answer it will be. Let's take an example. If the probability of a yes-no question, the probability of yes is 0, that means that you will never get the answer yes, then there is no uncertainty. You can easily guess that the answer will always be no. So for questions for which the answer is always no, the entropy is just 0. On the other hand, if there are equal probability for getting the answer yes and no, then there is very high entropy because it is harder to guess whether the answer would be yes or no. Let's now go back to the example where we were playing a game. The game is to answer the question, which card do you hold? That's your opponent hold. Initially, there are 52 possible outcomes in all, and each has the same probability, 1 by 52. The entropy at this point is very high. At this point, there are 52 possible choices for the question, which card do you hold? And all of them have equal probability. This is exactly the definition for entropy being high. If you had to calculate mathematically what the entropy is, this would be the sum of p of x multiplied by minus log p of x. So since we have 1 by 52 as the probability, this would turn out to be log 52. So at the beginning, before you've asked any yes or no questions, the entropy is very high. What happens once you ask a question? So once you ask a question, say for example, is the card an ace? You have two possible answers, yes and no. In both cases, the entropy has decreased. Let's parse this. If the answer is yes, you have 4 outcomes left. Each of them has a probability of 1/4 now of occurring. So if the answer is yes, you are left with 4 possibilities, each with the probability 1 by 4. Using our formula, the entropy turns out to be log of 4. Similarly, if the answer is no, the entropy turns out to be log of 48. Log of 4 and log of 48 are both less than log of 52, which was the entropy that we started out with. So overall, after we asked a question, we've reduced the entropy. We've reduced the uncertainty in our guess. Now, since the probability of yes is 4 over 52 and the probability of no is 48 over 52, using these two numbers, we can compute what the entropy is after we've asked our question, h of x given q1. So this will be 4 over 52 multiplied by log of 4, which is the entropy if you get the answer yes, plus 48 over 52 multiplied by log of 48, which is the entropy if you get the answer no. This entropy after you've asked the question, h of x given q1, is clearly less than log of 52, which was the entropy before you asked the question. So by asking a question, we have reduced the entropy in answering which card our opponent holds. And this reduction in the entropy is basically the information that you have gained. So to compute information gain, you will compute the entropy before you've asked the question and the entropy after you ask the question and take the difference. Let's relate it back to decision trees. In decision trees, at each node, you look at the value of an attribute. So you're asking a question, what is the value of a particular attribute? And the answer would be the value of that attribute. Whenever you ask a question, there is a reduction in entropy. So knowing the value of an attribute in a decision tree gives us some information, that is information gain. The more the information gain from a particular attribute, the higher up it will be in our decision tree. How do we say that the information gain is higher? In which case is the information maximized? As you saw in our card game, whenever we asked a question, two subsets are formed. Now when each of those subsets are homogeneous, they are most alike, the information gain is maximum. Let's take a look. If you had asked, is it an ace? Versus if you had asked, is it a black? If you ask the question, is it an ace? In both cases, both subsets, you're left with 26 outcomes. And both of those subsets are very homogeneous. In one case, you have all blacks and in the other, you have all reds. On the other hand, if you ask the question, is it an ace? You're left with one subset, which is very homogeneous, only aces, but the other subset has too many different types of cards. If you mathematically compute what is the information gain in each case, you will see that the information gain when you ask, is it a black, will be higher than the information gain when you ask, is it an ace? So, is it a black is the better question to ask. Well, we've spent a pretty long time talking about information gain and how to maximize it. The reason for this was that two of the algorithms that are used for decision tree learning use this concept of maximizing information gain. Let's cycle through those algorithms in the next class.